Now that we've defined what a linear contrast is, and we've written our original hypothesis about the means when the temperature was 5 and the mean when the temperature was 22, how do we use linear contrast for actually doing inference? So the hypotheses that we'll construct for a linear contrast, they look like this. The null hypothesis will always be the sum from I equals 1 to a of c sub I, our contrast coefficient for the ith level of our factor, times mu sub I, the population mean of the ith level of our factor. Is this equal to some particular value? We'll call it mu sub c naught. So in practice, this is usually 0. Versus our alternative hypothesis that the sum from I equals 1 to a of all of our contrast coefficients times the mu sub I is not equal to mu sub c naught. And it doesn't necessarily have to be two-sided here, but this is typically what it looks like. And again, mu sub c naught, that's just what we hypothesize this contrast is equal to, which in most cases is 0. So this is just like we've written before, just a slightly different notation. We can use this to perform a t-test. So to do a t-test, we first need to get an estimate for our contrast, which we called capital gamma here. But our estimate for this is going to be what we'll call capital C. C is the third letter of the alphabet, Roman alphabet, and gamma is the third letter of the Greek alphabet. So C is equal to the sum from I equals 1 to a of all the contrast coefficients times y sub I dot bar. So basically, we're plugging in the sample mean for the population mean. So our sample mean is our estimate for the population mean. So this quantity here, which we're calling big C, is our estimate of the contrast, and C has a normal distribution, and its expected value, the expected value of C, is equal to mu sub c naught, our hypothesized value for the contrast, if the null hypothesis is true, and the variance of C is equal to sigma squared divided by n times the sum of all of our contrasts squared. So summing from I equals 1 to a. So we know the distribution of C. It's just another random variable that follows a normal distribution with an unknown variance, and so a t-test is appropriate here. So we can construct our t statistic, t naught, which is equal to our C here, our estimate for the contrast, which I will write out as the sum from I equals 1 to a of C sub I times y sub I dot bar, that's the sample means, minus mu sub c naught, again that's just our hypothesized value for what the contrast is, and then we divide this by our standard error of our contrast here, the C. The standard error, remember, is the square root of our estimate of the variance. So we're going to plug in our best guess for sigma squared, and then we're going to take the square root of this. So our best guess for what sigma squared is in ANOVA is our mean squared error. So the standard error of our contrast is the square root of the mean squared error divided by n times the sum from I equals 1 to a of all of our contrasts C sub I squared. And this, if the null hypothesis is true, then this is going to follow a t distribution with big N, that's our total sample size, minus A, the number of levels of our factor, degrees of freedom. This is the same number of degrees of freedom that we have in the mean squared error here. We then use this T statistic to perform just a regular old t-test, just like we used before. We find the probability of observing a t random variable that follows big N minus A degrees of freedom that is greater than the absolute value of our observed test statistic, and we multiply that by 2 since it's a two-sided test. So let's give an example of how we would do this in the coffee case that we saw above. So I'm going to move on to the next slide here to show you that. So remember our null hypothesis for the coffee example was that 1/2 of mu1 plus 1/2 of mu2 plus plus negative 1/2 of mu3 plus negative 1/2 of mu4 plus 0 times mu5 was equal to 0. That's our null hypothesis here. So we can write out our contrast coefficients. We have C1 is 1/2, C2 is 1/2, C3 is negative 1/2, C4 is negative 1/4, and C5 is 0. So using this, we can find what our C is. This is our estimate for the gamma, and C, remember, is the sum from I equals 1 to A of all of our contrast coefficients times the sample means for each level of our factor I. So what will this look like? Well, C1 is 1/2 here, and what's our sample mean for mu1? What's our sample mean for recipe 1? That was 14.023. We'll add that to 1/2 times our sample mean for recipe 2, which was 18.421, plus negative 1/2 times our sample mean for recipe 3, which was 18.004, plus negative 1/2 times our sample mean for recipe 4, which was 22.746. And then our fifth term is 0, so we won't write that. This comes out to negative 4.153. So this right here is our estimate for the contrast that we're interested in. Basically, is there a difference in the average of the coffees brewed at a temperature of 5 degrees Celsius and the coffees brewed at a temperature of 22 degrees Celsius? So this gives us the numerator that we'll need here in our test statistic to calculate the T statistic. We have the hypothesized value, that's 0. We have the contrast and we have the sample size, but we don't have the mean squared error. And this data set, we weren't given the raw data. However, we were given the sample variances. And we know that the mean squared error is a weighted average of the sample variances. And in this case, all of our sample variances have the same sample size. So all of our samples have the same sample size. So for us to calculate the mean squared error, we just need to take an average of the sample variances. So the sample standard deviation for recipe 1 was 3.434. So we'll square that to get the sample variance. Then we'll add it to the sample standard deviation of recipe 2, 0.686. Square that to get the sample variance. The same for recipe 3, 4.765. squared plus the same for recipe 4, 0.687 squared, and then 3.711 squared. This is the sample variance for recipe 5. And then we'll take all of this and we will divide it by 5 because we have 5 levels of our factor here. Why are we using the sample variance for recipe 5 when it's not involved in our contrast? Well, if we assume that the population variances across all of our groups are the same, then we can take the variability in our data for recipe 5 to help us to get a better estimate of sigma squared. So we can still use it even though we're not interested in mu sub 5 here. So this comes out to 9.842. All right, so our T statistic, now we can calculate that. We have the numerator here, we've got negative 4.153 minus the hypothesized value for the contrast, which is 0, divided by square root of our mean squared error. So that would be 9.842 divided by n, which was 3, we're assuming, times the sum of all the contrasts squared. So if we take our contrast, they're all 1/2 or negative 1/2. We square them, we get a quarter, and then we add all those up. We have 4 quarters that we're adding up, and so that adds up to 1. Our T statistic is therefore negative 2.2929. So what is our p-value here? So our p-value for this test is the probability that we would observe a random variable that follows a t distribution that has n minus 1, big N minus 1 degrees of freedom. How many is that? Well, let's figure that out. So we have big N equals A times little n. We have 5 levels and 3 observations for each level, so that's 5 times 3. That would be 15 observations total. And again, A is 5, so big N minus A would be 10. That's our number of degrees of freedom we have for our mean squared error, and that would be the degrees of freedom we have for our T statistic here. So a random variable that follows a T distribution with 10 degrees of freedom, probability that's greater than the absolute value of our T naught. And we would multiply this by 2 because it's a 2-sided test. So this comes out to 0.0448. So it looks like we have moderate evidence against the null hypothesis here. So what would we conclude? We would conclude that it appears that there's some evidence that there's a difference in the mean strength of coffee that is brewed at 5 degrees Celsius compared to coffee that is brewed at 22 degrees Celsius.